Okay, so our next speaker is Natalie Paquette, who's going to tell us about 4D physics from 2D chiral correlators.
Okay, can everyone hear me? All right. Well, I'd like to start by thanking the organizers for inviting me to speak at this wonderful conference and in such a beautiful city. And today I'll be reporting on work done in collaboration with Kevin Costello based on 2 papers that appeared on the archive this past year. Oh, there we go. So the work that I'll be talking about today arises from a confluence of progress in a few different subfields where we see similar formal structures appearing in very different guises. And some of the fields that are implicated in the study today include the conformal bootstrap, the celestial holography program, about which you'll hear much more at this conference, and also a field that I've been working on for the past couple years now called the twisted holography program or correspondence, where one tries to study toy models of the ADS-CFT correspondence from a top-down perspective, leveraging the open-closed duality in twisted or topological string theories. So in all of these areas, we see the same formal structures emerging. In particular, we see chiral algebras, which are most familiar to us perhaps as the holomorphic symmetry algebras inherent in familiar 2-dimensional conformal field theories. But in recent years, we also know that there are many other physical arenas in which they arise. For example, as at least classical asymptotic symmetry algebras for various theories in 4-dimensional asymptotically flat spacetimes, as well as protected subsectors of higher dimensional supersymmetric theories that one can access by means of an appropriate supersymmetric twist. And similarly also in twisted string theories, for example, after applying a supersymmetric twist, they arise as protected subsectors on the world volume theories of the corresponding D-branes. And quite similarly, we also see holomorphy over and over again. Of course, chiral algebras themselves are holomorphic. And similarly, both the open and closed or bulk boundary theories that are implicit in the twisted holography program are holomorphic theories, meaning they only depend on the complex structure of the metric in the underlying spacetime rather than on all components of the metric. So perhaps even though these various subfields appear very disparate, there might be some fruitful connection underlying the physics, at least at the level of universal or symmetry-protected structures, where these special mathematical constructs appear, whether that be universal or symmetry-protected physics arising by studying infrared physics or the corresponding soft sectors, or whether it be supersymmetry-protected or BPS observables that one can access by means of an appropriate twist. So what I'll tell you about today uses as a particular unifying structure to explore some of these connections a local holomorphic theory in 6 real dimensions, and in particular it will live on twistor space, which is a 6 real dimensional manifold. So I'll be studying a particular local holomorphic theory on twistor space, and the 6-dimensional theory will serve as a natural bridge between some 4-dimensional physics and some 2-dimensional physics, or at least an algebraic structure. So to any local holomorphic theory on twistor space, we can associate 2 corresponding structures that turn out to be deeply related to one another. On the one hand, it's been familiar for a very long time, since the advent of twistor theory itself, that one can use a local holomorphic theory to obtain a 4-dimensional theory by means of the classical Penrose transform. And in particular, one can access conformal or massless physics from a local such theory, and I'll be focusing indeed on massless or conformal physics in my talk today. What's perhaps a bit less familiar is that to such a theory, one can also construct a 2-dimensional chiral algebra by means of a construction called causal duality, which I'll explain in the bulk of my talk. So this works for any local 6D holomorphic twistor theory. I'll focus on a particular one today by means of illustration. But from this perspective, Kevin and I proved an isomorphism between correlation functions in our 2-dimensional causal chiral algebra and form factors in the 4-dimensional theory. Now, the four-dimensional theory is conformal, so we're not going to study scattering amplitudes in such a theory, of course, but instead we'll be studying form factors, which are scattering in the presence of local operator insertions. So one can get non-trivial scattering from that point of view, and that's the quantity that's isomorphic to 2D chiral correlation functions in this algebra. And for the particular 6D theory that I'll focus on in this talk, the form factors in that four-dimensional theory will actually enable us to reproduce some very familiar QCD scattering amplitudes for scattering of gluons. And so we'll recover some very famous and familiar formulas from this point of view as a nice little bonus from this construction. So before I get into the particulars of the theory that I'll be focusing on, let me just remind you what's about the nice features of these 4D twistorial theories, meaning 4D theories that arise from local uplifts to six-dimensional theories on twistor space. And I'll refer to Kevin's talk at Strings last year for many more of the details of these kinds of constructions, for example. So 4D twistorial theories are extremely rare and extremely special. There are very, very few examples of such theories that are known, and because of their specialness and the specialness of their construction, they exhibit very particular and unusual properties that you would not see in a generic four-dimensional theory. And those special properties, in particular very, very strong analytic constraints on the observables of these four-dimensional theories, can be naturally derived from their six-dimensional origins, and in particular basic facts about the geometry of twistor space. So let me just state the basic facts for you that we'll need today. So I'll remind you about twistor space, first of all. It's given by this non-trivial fibration of two line bundles over a CP1 or a two-sphere. And throughout this talk, I'll use Z to denote my local holomorphic coordinate on that copy of CP1. And as a real manifold, twistor space is equivalent to R4 cross CP1. So to every point in our four-dimensional space-time, we can associate a copy of CP1 or a complex line or a two-sphere in twistor space. And the basic fact about the geometry of twistor space that we'll need today is quite simply, given two copies of CP1 associated to 2 points in 4 dimensions, say x and y, those two spheres will only intersect in twistor space if and only if the corresponding points in 4 dimensions are null separated. Now, in twistor space, it's also quite natural to work in analytically continued four-dimensional space-time because the observables of twistorial theories can be analytically extended to entire analytic functions. At the end of the day, one can, of course, take various real slices and specialize to the space-time signature that one is most interested in, but I'll work in the analytically continued picture for today. It's just a remark. But the important consequence of this basic geometric fact are that correlation functions in our 4D twistorial theories are entire analytic and in fact rational functions with singularities only on the analytically continued light cone and nowhere else. And one can also prove, basically as a consequence of this fact, very special and essentially integrable properties of these 4D theories. So this is all just to emphasize that their observables are very, very simple analytic functions under very good control, and that comes from a six-dimensional point of view. Finally, the last kind of bit of twistor lore that I just want to briefly remind you of before we get to the specifics is the classical Penrose transform, which tells us how we can build from very simple geometric objects on twistor space natural holomorphic massless field configurations in 4 dimensions. And one does this by constructing Dolbeault cohomology classes on twistor space, wedging them with a corresponding volume form. And if you take those differential forms that we can construct very readily and integrate them over the CP1 of my twistor space, I'll land on massless field configurations in 4 dimensions, in particular on-shell configurations in 4 dimensions. And so twistor space provides us a very convenient way to geometrize solutions of, in general, nonlinear massless field equations in 4D. And so that's really, again, a great boon to us when we want to study these twistorial theories. So that's just a brief review of the important properties that I'll make use of implicitly in the rest of the talk. So here, Just to summarize is the picture of my talk. I'll have a local holomorphic theory on twistor space. I can reduce along the CP1 in twistor space to obtain a certain four-dimensional theory in 4D. And we'll see that the one that I'll be studying today is given by a coupling between self-dual Yang-Mills theory and a certain real scalar field that I'll call an axion. And on the other hand, I can study a certain chiral algebra on that same twistor sphere, supported on CP1, by means of Cazul duality, or what we sometimes call a universal defect on CP1. I'll explain what that means. To, on the other hand, obtain a two-dimensional chiral algebra supported on the twistor sphere. And because everything in sight is holomorphic, this whole construction really looks like it's begging for an uplift to a 10-dimensional string theory picture, at least in a twisted context. And I think that's a promising hope for the future, but I don't have anything more to say about that for today. But that's just a hope for the ultimate context of some of this work. So now let me get into the specifics. What is the particular twistorial theory that I want to be studying today? So let me just start with the gauge sector. So first, on twistor space, I'll be studying a holomorphic version of BF theory, which is a function of two fields that I'm calling curly A and curly B. So A is a holomorphic gauge field. It's a 0-1 form, or a partial connection on twistor space. Curly B is a 3-1 form, and both of these fields satisfy gauge symmetries, which I haven't written down, but they correspond to positive and negative helicity states, respectively. Positive for curly A, negative for curly B. And if I integrate this theory over CP1, it's been known for a very long time that what I'll land on is self-dual Yang-Mills theory in 4 dimensions, again with states of both helicities, that satisfy the usual BF action, where now B is an anti-self-dual 2 form in my conventions. Now, you also might know that if I were to add a deformation term to the self-dual Lagrangian proportional to trace B squared, I would land on something that's perturbatively equivalent to ordinary Yang-Mills theory, just written in a first-order formalism, but I'm not going to do that today. Instead, although this is the starting point for my twistorial theory, I'm actually going to need to augment it by another sector. And the reason is because self-dual Yang-Mills theory, although it's a twistorial theory classically, again, this is a well-known old correspondence, it fails to be a twistorial theory quantum mechanically. And the simple reason for that is that the 6-dimensional theory does not exist as a good quantum theory in 6 dimensions. Why is it not a well-defined quantum mechanical theory? Well, it suffers from a one-loop gauge anomaly encoded by this box diagram. So if we want to study a 4D theory at the quantum level that has all of these nice twistorial properties, I'm going to need to repair this situation and cancel the gauge anomaly in 6 dimensions so I have a well-defined 6D local theory. And indeed, this anomaly can be canceled, as has been shown by these authors, by a Green-Schwarz-like mechanism, where we add a particular sector with a new field whose tree-level exchange will precisely serve to cancel the one-loop gauge anomaly, as is usual in Green-Schwarz. And in particular, that works for these gauge algebras. One can also study other gauge algebras if you add matter, but I'm not going to do that today. But in any case, we know what we have to do per these papers in order to cancel this particular anomaly. So in 6 dimensions, we will add an additional sector to our theory. I'll be brief on the details in view of time, but the important thing is that we add an extra degree of freedom that couples to the gauge sector via a Chern-Simons term, and the coefficient is precisely tuned to get this anomaly cancellation to work. Perhaps more importantly for my purposes today, when I reduce the 6-dimensional sector down to 4 dimensions, I'll end up with a real scalar field that I call rho, coupling to an F-wedge F term, which is why I'm going to call it the axion for the rest of this talk. And it also has a particular quartic kinetic term. And these real scalar fields with quartic kinetic terms might perhaps be familiar to you in other contexts where they appear to cancel conformal anomalies in 4 dimensions. So when the dust settles, my full theory is some 4D conformal field theory given by self-dual Yang-Mills coupled to my quote-unquote axion field. So that's the theory of interest to me today. So just to kind of set the stage and get us on the same page, let me think very briefly about the diagrammatics of what's going on here. So self-dual Yang-Mills on its own has these schematic Feynman rules, where I have a plus-minus propagator and a plus-plus-minus vertex. And the scattering or the dynamics of self-dual Yang-Mills is famously a little bit impoverished. It's a one-loop exact theory that only has a one-loop diagram for all plus scattering of gluons. Of course, one can get a little bit more mileage out of this theory if one were to compute form factors. So for example, I might be interested in computing scattering in the presence of the local operator insertion trace b squared, which remember is that term that I can add to the Lagrangian to get back full perturbative Yang-Mills. So at the level of diagrams, this would give me an extra bivalent vertex like so. And that would enable me to compute from form factors of self-dual Yang-Mills a larger class of QCD amplitudes given by a prescribed number of negative helicity gluons and an arbitrary number of positive helicity gluons. Now, just to be precise, normally when one computes these kinds of quantities, I would integrate over the space-time position of my local operator insertion. But from the Twistorial or the Chiral algebra point of view, for my purposes, it's actually more natural to study the corresponding quantities at fixed positions of local operators. So really what I'll be computing is a kind of unintegrated version of these form factors or integrands. So when I say form factors for the rest of the talk, that caveat is to be understood. Okay. Now, again, my 4D theory is, of course, not just self-dual Yang-Mills theory on its own, but it has this extra axion field that's coupling to it, and that gives me an additional vertex if I want to think a bit diagrammatically, and effectively this vertex starts coming into play at the one-loop level by the Green-Schwarz mechanism, so that would how I would account for axion insertions. So the form factors that we computed in our paper and that I'll be telling you about today are fairly simple. I'll just consider a single insertion of a local operator at the origin. Of course, one could hope to apply this much more generally and consider form factors with many operator insertions. In doing so, one would have to contend with the four-dimensional OPE of my 4D CFT. Because in particular, the OPE coefficients in 4D would start dressing the chiral correlators if I were to try and compute more sophisticated amplitudes. I'm not going to tell you about that today, but I'll just mention that because the 4D theory is twistorial, those functions would still be rational and of course constrained by associativity since it's still a CFT. So I expect that will be an interesting way to make progress in the future. But for today, let's just focus on some simple form factors given by inserting some prescribed local operators at the origin in 4 dimensions. So what I want to do is start by just telling you the answers for the things that we computed. So here are some form factors in our 4D theory. We computed them by computing correlators in a 2-dimensional theory, and I'm going to tell you the answers. And then for the rest of the talk, I'll introduce what my chiral algebra is and how we actually constructed it. And that's really the object that we use to compute these things. Okay, so here's what we got. Just a few words on notation. Null momenta, I'll parameterize as usual in the spinor helicity formalism by lambda lambda tilde, where lambda is related to the holomorphic coordinate on the celestial sphere at asymptotic null infinity in this way. And that celestial sphere is to be identified, and the holomorphic coordinate is to be identified also with my twistor sphere that I've been talking about throughout the talk and that I'll continue to talk about. So I've already written these form factors in a manifestly 2-dimensional notation. So this is what I have. Here denotes the local operator that I'm inserting at the origin. J tildes correspond to negative helicity gluons, and the J's correspond to positive helicity gluons. So in my theory, first at tree level, if I insert a single copy of trace b squared at the origin, and steady scattering with 2 negative and arbitrary positive helicity gluons, what can I reproduce? Well, of course, I have to obtain the Park-Taylor formula for color-ordered tree-level MHV amplitudes. And that's indeed what we recover from a 2D computation. Similarly, for three J tildes, three negative helicity states and arbitrary positive helicity states, we recover the formula for tree level NMHV amplitudes in a CSW-like form, where the answer factorizes, for those familiar with those kinds of expressions. We also computed a few things at one loop, where of course our axion field really comes into play in an important way. At one loop, with a single insertion of trace b squared at the origin, there's now a non-vanishing answer for one negative helicity state and arbitrarily many positive helicity states, and we computed it, and we get this extremely simple and compact form of the answer. So you can see that the axion is really simplifying our life here and giving functions with very nice analytical properties relative to what one would be getting for the corresponding quantity in full QCD, not coupled to any axion. The axion's really canceling a lot of messy stuff here. Finally, I think it's also important to mention that trace b squared isn't the only local operator I can insert in 4D. Another interesting choice would be inserting this axion operator. And at one loop, if we study an all plus type form factor, we're able to reobtain the classical all plus one loop amplitude for self-dual Yang-Mills theory. And that's quite natural because our four-dimensional theory, being a CFT, has no non-trivial scattering. By construction, the axion is canceling the one-loop all-plus gauge anomaly in this setup. So if we insert a local operator whose whole role in life is to cancel the axion exchange in 4 dimensions, what could be left over? Well, only the all-plus one-loop amplitude that we can extract through this form factor. So the axion, again, is a nice way to kind of extract gauge theory answers by this construction. Okay, so now I need to tell you where the chiral algebra comes from in the remaining time, and I'll do so in a few steps. So first, where are the generators of the chiral algebra coming from? Well, quite simply, we get them by just studying on-shell background field configurations that are localized at points on my twistor sphere. So curly A corresponds to what I call J, which again were positive helicity states. Similarly for B, curly B, we'll get J tilde, and we also get 2 towers from the 60 uplift of our quartic axion. Now, this distributional gauge field configuration also turns out to be a conformal primary state under a natural action of the Virasoro algebra of negative integer conformal weight. So I can use the Penrose transform and integrate this thing over CP1, and I'll land necessarily on a 4-dimensional on-shell gauge field configuration that is also in a conformal primary basis with the negative integer conformal weight. And celestial holographers have told us recently that this corresponds to so-called conformally soft modes in 4 dimensions. So that's what these generators are from 4D. In form factors, I also use this notation, which is just resumming them with appropriate powers of energy to get back to the momentum eigenbasis, which is really where we are most comfortable doing our scattering. So here is my chiral algebra in terms of generators, again, of mostly negative integral conformal weights. So I have some very strange non-unitary structure here. Correspondingly, because I have a non-unitary chiral algebra, I'm not going to have a unique way to define correlation functions in my algebra that are consistent with the OPEs. Rather, there's going to be a family of conformal blocks, and so a family of ways of defining correlation functions. The analogy to keep in mind here is the WZW chiral algebra living on the boundary of 3D Chern-Simons theory, which also admits interesting conformal blocks. And indeed, this chiral algebra is best thought of as the boundary chiral algebra for a 3-dimensional theory. But in this case, the 3-dimensional theory is not topological. It's what's called a holomorphic topological theory. These kinds of things are known to arise as twists of 3D n equals 2 theories. And we can also get this 3D theory from twistor space. And that works as follows. Let me take twistor space and remove the CP1 corresponding to the origin of R4. I get this manifold, which I can reduce on CP1 as usual. By construction, I'll get R4 with the origin removed. And I can quantize my 4-dimensional theory on this space and obtain the Hilbert space of states of my 4D theory on S3, which by state operator correspondence is the space of local operators of my 4-dimensional theory. But on the other hand, I could equally well reduce on S3 And the result is a three-dimensional theory, and I'll refer you to the paper for the details of this 3D theory, that's holomorphic topological, and it's supported on CP1 cross R. And if I radially quantize that theory, I'll obtain or I'll get one definition of the space of conformal blocks for my 2D chiral algebra. And Kevin and I proved that in fact these spaces are isomorphic to one another. So that was my notation, that a local operator in 4D inserted at the origin corresponds to a conformal block. So my correlation functions are perhaps best thought of as correlators in a bulk boundary system where I choose a state in the 3D theory at 0 and the holomorphic boundary condition supporting the chiral algebra at infinity with some local operator insertions, and I pair them. So I'm short on time, but let me be very brief and tell you about the OPEs of this chiral algebra, and then I'll conclude. So I simply need to study generalizations of gauge current couplings. These are holomorphic generalizations of familiar AJ couplings that are supported on CP1. And all that I ask is that these couplings are consistent with gauge invariance of my theory. That will lead to non-trivial constraints on the OPE. It will lead to an OPE among these putative current algebra generators. And at tree level, what I get is nothing but the current algebra for the gauge symmetry of my theory. What else could I possibly get by imposing gauge invariance on these source terms? And this is just what we call the universal or Koszul dual chiral algebra. But the key point here is that in these holomorphic or twisted theories, these algebras also admit non-trivial but computable quantum deformations. And so you actually get very interesting deformed chiral algebras at the quantum level from this prescription. And I'll refer to a paper I wrote with Williams for more details of how we get them, and to papers with Costello for applications in twisted holography. So this is my kind of universal algebra. Any 2D holomorphic theory, say a bunch of chiral fermions that I might want to couple to my 6D theory along the twistor sphere, has to live in a representation of this general structure. Here are the OPEs. We computed them at tree level. I'll just remark, if you turn off the axionic towers, you'll recover a level 0 Katz-Moody algebra that's known to be the asymptotic symmetry algebra in 4-dimensional gauge theory. And we also computed the quantum deformations presented here. The coefficients turn out to be fixed by the twistor anomaly in 6 dimensions. And very briefly, let me just point out that the OPE limit in the 2D chiral algebra corresponds to a collinear limit in 4 dimensions because of the identification of the celestial sphere with my twistor sphere. And so these corrections are related to one-loop collinear splitting amplitudes in gauge theory. I can say more about that afterwards if you're interested. And I know I'm out of time, so this is my conclusion slide. The main theorems that we proved, to sum up, are that there's a correspondence between our 2D chiral algebra and our 4D theory with conformal primary generators mapping to conformal primary states, conformal blocks to local operators, and ultimately correlation functions to form factors. For the future, of course, there's much to think about. I have work in progress with Costello and Atul Sharma considering a different 6D theory from a more top-down twisted string point of view. I'm also studying magnetic monopoles and the consequences for the representation theory of the chiral algebra with my postdoc, Nick Garner. Because everything I said works for any local holomorphic twistor theory, you can run the same program in self-dual gravity. And I'll just point out this upcoming heroic work by these authors showing how to cancel that twistorial anomaly in the gravitational case. And finally, I hope there will be more to say in the future about more general QCD amplitudes by exploiting these kinds of anomaly canceling considerations. So apologies for going over. Thank you very much for your attention.
Thank you very much. We're a bit short of time, but we could take some quick questions. Kumran.
Very, very nice talk indeed. Just a comment.
Yes.
Many elements of what you're saying connects nicely with the n equal to 2 strings. And in that context, maybe the connection to your talk would be the axion played the role of self-dual gravity already. Mm-hmm. That is, the axion gets mapped, I believe, to the scalar field that is Plibansky's formulation of self-dual gravity. So I think it would be very natural to combine them.
Absolutely.
In that context. And the Twistorial sphere arises in that context by having an n equal to 4 supersymmetric algebra which has a twistor sphere in it.
Yeah. Yeah, thank you very much, and I should have noted that. I don't fully understand the connection yet, but I'd love to talk with you more about that. Indeed, it's very clear that all of the circle of ideas have to be related to one another. Absolutely.
Any more questions? Okay, well, we're out of time, so perhaps we should stop there and thank the speaker again. And now a brief organizational announcement.
Okay, so this was our first session. Thank you, all the speakers and the chair. Now we will have our first coffee break. Now, to give you some orientation, the coffee break will be approximately in that direction.